little strange for me. I don't usually need a microphone when I'm teaching, so you may have to adjust it because I probably sound like I'm screaming. So it's a pleasure to meet all of you and visit Maryville today. I've driven past it many times, but never taken the opportunity to see the campus. I might add that I started out my career in Texas as an undergrad and did 3 years undergraduate research, and then did a few internships between there and graduate school. And those who are motivated and very interested in chemistry, there are a lot of opportunities to do so at UMSL, potentially other regional institutions, and I encourage everybody to do so. A lot of my work resulted in 6 papers undergrad. And so with grit, determination, and intestinal fortitude, you have many opportunities available beyond the St. Louis region, and I encourage everybody to think accordingly. Now, when I moved to UMSL, one of the primary drivers for that was use facilities available that weren't easily obtained at Kentucky. And so I think I have to point to that one. All right, so all of these people down here were collaborators for a number of years, and until I was able to obtain an instrument critical to our studies, a magnetometer, we sent everything to France to get our measurement. And so you can imagine takes a lot of time to do so. And so this is a culmination of probably 20 years worth of work. And I'm only giving you a few highlights, but suffice it to say, we're self-sufficient now and can do all the measurements in-house that we relied on external collaborators. And since I run a small group, primarily of undergraduates and a few graduate students, everything's hands-on. A lot of learning opportunities there. All right, so in terms of one of the projects we work with many. One is magnetic materials. You might have heard of quantum computing, qubits, things like that in the literature or at least in the news. We're also working on that, but for time considerations, I'm talking about a more a general topic. In this case, it's going to be photochromic materials. So you can imagine these photoresponsive materials, if you have a material that will change its properties as a function of some input, some stimulus, be it either electrical, light, temperature, what have you, you can toggle between 2 or more states. You have the basis for logic circuit, at least in a binary information storage standpoint. So in our particular case for this project, our input's going to be light or temperature change, and our output's going to be either a change in magnetism or color. Right, and we can easily detect that spectroscopically, even with our eyeball spectroscopy. So we look to a historic compound. It's also known as Prussian blue. This has been known for 300 or more years as a pigment. Many artisans in Europe discovered this 300 plus years ago, and you can substitute at a variety of metal sites in this structure. This is an idealized structure, but composed of many defects in these hexacyanoferrate 3 sites, red spheres. These average defects are throughout the structure, and they give what's called a ligand field, which changes things such as magnetism, color, what have you. And so by getting the stoichiometry just right, the phase of the moon, and other things, aging, many people can, in principle, make compounds that have predictable magnetism and whatnot. But being 3-dimensional materials that are insoluble in solvents, they're not particularly fun to work with. So we decided to take the idea of this tunable structural archetype and mimic them in terms of molecular species so that we could better understand the properties behind what's going on. And so when you get the synthesis and the conditions just right, and you have an average N5O coordination environment around the cobalt, you have a proper ligand field. If you assume everything's octahedral geometry, you have non-bonding T2G symmetric orbitals. That's the DXZ, the DYZ, and the DXY. Those are non-bonding with respect to metal ligand bonding. The EG set are anti-bonding with respect to metal ligand bonding, and these are composed of the dx squared minus y squared and d. So when you have electrons in the non-bonding orbitals, you don't really change the bond distances. those species, but when you do populate the EG orbital set as being antibonding orbitals, you dramatically change the electronics and the metal ligand bonding. You usually elongate the metal ligand bond. And this is going to become very important in the theme later. So in this particular compound, if you get it just right, you have two different states composed of low spin iron 3. That means or rather low spin iron 2. You have 6 paired electrons. And when all the spins are paired, that's called diamagnetic. Likewise, you also have cobalt-3 low spin, 6 electrons total. They're also spin paired, diamagnetic. When you increase the temperature or shine light on it, you affect a single electron transfer between the iron 2 to generate an iron 3. So you remove a T2G electron and you transfer it to the cobalt-3. And with the spin state change going from all electrons here to electrons populated here, you have a high spin state, you get a cobalt-2 state. All right, so in other words, to summarize, you're going from 0 unpaired electrons to 4. Right, so the magnetism has to change a lot. And because you're putting electrons in the antibonding orbitals on cobalt, changing the cobalt nitrogen distances, you're also dramatically changing the color of the material, this metal cyanide metal unit. So if you've had a basic electron transfer theory, you can use something called Marcus-Husch theory to explain and parameterize different factors necessary for doing electron transfer. So I like to tell my physics colleagues that I have an equation, so the problem's solved. I just need to know which parameter to change. From a synthetic standpoint, that's rather difficult, but we think about it in simple terms in that you have two electronic states, slower than I'm used to, but I'll slow my baud rate. These two electronic states have a difference in potential energy described by delta G standard. You have an effective energy barrier between those two states. So in other words, you can't just climb or directly go between the two states, you have to climb a hill. Right? You have something called reorganization energy. This is blue lambda. That's the cost of doing business, in that if you change the oxidation number of your metals, change the Lewis acidity or basicity of everything present, and you get breathing of that unit. That breathing requires energy, it requires time, and if you're expanding and contracting the volume of that unit, everything around it has to accommodate that change. Cost energy. All right, and then up here is the Wild West in terms of what happens when you shine light on the material, and we're still working to understand that. But suffice it to say, we have delta G, we have a reorganization energy, we have an effective barrier, this electron transfer, and if you can tune everything systematically, then you can start to design materials. Preferential property determination. So if you look at the archetypal Prussian blue, composed of hexacyanoferrate 3 and cobalt-2 centers, at room temperature, you have a purple material with lots of unpaired electrons. And so this is that species here. Everything has unpaired electrons, and you have an average stoichiometry. When you lower the temperature below a critical temperature, in this case around 250 or so Kelvin, it adopts a blue coloration, and you can see that now you've got mostly cobalt-3 and an iron-2 spin paired center. The magnetism drops. Now, if you shine light on the material, it's photoactive. That light will cause back electron transfer and regenerate this purple state, which is composed mostly of paramagnetic centers. So in doing so, you get a very large enhancement to its magnetic signal. This large enhancement is different than molecules in that below 19 Kelvin, this material undergoes long-range magnetic work. In other words, if you had a really cold refrigerator, it would stick to it. Right? Above 19 Kelvin, you have too much thermal energy. This long-range magnetic order goes away, and now you have paramagnetic spin centers. Those paramagnetic centers are uncoupled because there's too much thermal energy for them to spin pair. And then if you increase the temperature further, this collapses down to a diamagnetic state where you've gone back to low spin cobalt-3 and low spin iron-2, no unpaired electron. And then as you go up further again, you recover your electron transfer again, and you get into this regime up here. And depending on if you cool it or heat it, you get something called thermal hysteresis. That's that sigma-shaped thing up at high temperature. And the width of that is indicative of you have long-range cooperativity in terms of this breathing of the material. And that if the bonds are getting bigger, things have to move, takes time. And if it shrinks, it does it as well, takes time and energy. All right, so to the chemistry part. The chemistry part is such that we wanted to simplify the problem such that we have molecular units. Think of them as small pieces of that three-dimensional solid. And through various chemistry approaches, we can control the nuclearity and number of spin centers coupled to each other. Doing so, we can say a lot about the cost of doing business from an electron transfer standpoint and why does the color and magnetism change. More importantly, why does it do it systematically? So instead of using 6 cyanides around an iron 3 spin center, we decided to simplify the problem, remove 3, and put a tridentate ligand, an organic molecule with a 1- charge, that takes the place of those 3 cyanides. It reduces the overall charge of the complex. And now we have a scaffold in that this ligand can be substituted at up to 10 chemical positions, including the boron and the R group. R could be any alkyl or what have you. The idea there is you simultaneously tune the steric properties, that is the size of the ligand, the electronic properties, that is, does it serve as a donor or acceptor in a Lewis acid base. And by changing primarily those positions down there, the so-called 3 positions labeled Z, you can change how the cyanides bridge to adjacent metal center, and you can control that from anywhere from 1 to 4, depending on the metal ion and number of cyanides present. All right, what does this do for you? Well, this allows you to get a lot of papers, a lot of results. These are just a few to convince you that once you understand the rules for self-assembly and how to connect metal centers to cyanide bridges, you can now start to think about, do I feel like making a trinuclear complex on a Tuesday on my left foot? Yes, I can do that. Or if I want to make a square, I can do that by proper ligand and metal choice. And by understanding these so-called self-assembly reactions, we can predict and tune the properties and have some reasonable outcome for our predictions that we can systematically measure and compare to other structures. I'm going to spend today talking about the photochromic materials, some of which are boxes, most of which are squares, but you can also make trinuclear, dinuclear, hepta, nana, whatever nuclear you want to pick for that day by playing the ligand substitute. All right, so to give you a little bit of coordination chemistry, hopefully everybody likes coordination chemistry. I do. By changing the number of donor constituents on these arousal borates, you can change how good of a donor or acceptor it is. Twice as to say is when you have a dependent pyrazole here and 3 unsubstituted pyrazoles attached to a common boron. Those are electron deficient ligands, so they're not very good Lewis bases. When you substitute 3 alkyl groups onto the pyrazole, it's become very basic, and they become very good Lewis bases in comparison. And somewhere in the middle, you can go between these 2 extremes to your heart's content. Yes, you can put in fluorinated groups. Oh, we're doing that. The chemistry is a little bit more difficult. If you're interested, come talk to me. You could work on it. All right, so just summarizing up a little bit of data, we spent a bit of our time doing spectroscopy in that we want to figure out what are the donor acceptor properties of our ligands. And if you look at the x-axis here, we're looking at cyanide stretch for that complex in solution. And you can see, since I can't see that screen from here, very electron deficient tetrapyrazole borate has a very high energy cyanide stretch, suggesting that not much electron density is getting into the cyanide. C n triple bond, spending most of its time on the iron. Alternatively, if you look at the TP star methyl, where you have 3 methyl groups at the X, Y, and Z position, you can see that the cyanide stretch very low in energy. That's suggesting that the ligand is serving as a very good electron. Right, and in this axis is just the absorption energy required for charge transfer between the ligand and the metal, so-called ligand to metal charge transfer. These are very dark and intensely colored materials, and it's because of that electronic transit. I'm not going to focus on that. But I will focus on the cyanide and the borohydride stretches because what's counterintuitive is that the most electron donating of the series tend to give pH stretches that go in the opposite direction energy-wise. It's the cyanide. So while many people would think that these ligands are just there for the ride and they're taking up space, they actually serve a critical role in the electronic and magnetic property. In that if the cyanide goes to high energy, that means you're not putting much electron density into CN triple bond. But in the opposite sense, it's going to the BH bond stretch. And so as one goes up, the other goes down. You get a push-pull type electron density. Right. So this allows us to do a lot of really cool chemistry. If you look at the electrochemical potentials, things that have lots of donor groups on the prazoborate tend to give very large and negative E1/2 potentials, meaning E1/2 is defined as the energetic cost voltage-wise, reducing the iron 3 to iron 2 reversal. So the so-called iron 2,3 redox couple. And so for very electron deficient ligands, such as these, you can see that it's a much more positive potential, meaning it's much easier to reduce that iron 3 to iron 2. And that's going to become important. But summarizing a lot of the data, as you decrease the donor ability of the prazoborate ligand, you increase the cyanide stretch, at least in solution. You increase the energy of that charge transfer absorption called lambda max. That's the energy of it, and you decrease simultaneously energy of the BH. All right, for those who like density functional theory calculations, you can do that. It gives you additional information about where things are energy. And summarizing up a lot of data, very good electron donors have a very close separation between the ligand-filled orbitals and the empty metal-based orbitals, and it gives you a very low energy lambda max. And you have a big energy difference between those orbitals. You get a high energy lambda max, and so that explains the color that we see with all these. Also related to the magnetism. All right, so in terms of our first model complexes, we decided to start off simple and make molecular boxes. So we used tridentate capping ligands. The iron, in this case, the tetraprazoborate. 3 of the pyrazoles are coordinating in a cis fashion to each other. That is 90 degrees between the nitrogen atoms, the iron, to give this tricyanoferrate 3 anion. In the presence of cobalt-2 perchlorate, and then subsequent addition of another tridentate ligand, trisparazoyl ethanol, you can make these molecular boxes, tetracationic overall, and because of games we played with the ligand choice, we could get an X-ray structure. We had to choose hydrogen bonding on the cobalt site because anything with an alkyl group would co-crystallize in the same manner as the iron. We couldn't differentiate the iron and the cobalt. So we had to take advantage of intermolecular hydrogen bonding between that terminal alcohol and its neighbors and lattice solvent to actually get a good X-ray structure. In other words, if you don't have a good X-ray structure, you don't get published. Right? So this is what the molecule looks like. It's the cation. In terms of its infrared spectra, we're looking at the energy it takes to vibrate a bond. In this case, we're looking at cyanide stretches, so doing this. Right? If it's electron deficient, that means you have a high energy cyanide stretch. If it's electron rich, then you have a low energy stretch, defined by its wave number. So at 298 K, we have iron 3 cyanide bridge to cobalt 2 high spin, meaning we have 1 unpaired electron on iron, 3 on the cobalt. That's a very high energy stretch. When you lower the temperature, you do electron transfer. Now you generate iron 2, you reduce the iron oxidation state by 1. You've increased the oxidation number of cobalt by 1. Get a corresponding low energy stretch. Now you get 3 of them usually. That's a current active area of research in that it's not just a simple one-to-one conversion as you might expect. There are other vibrational modes involved in the iron 2 cobalt 3 state that we fully understand. And we're using a new spectroscopic technique called two-dimensional infrared spectroscopy to look at that. All right, in terms of the color properties of this material, I'm showing you just a generic color wheel. In that complementary colors are related to each other by whether or not they're absorbed, reflected. if you absorb red, then the material would appear what in color? Green. If you absorb green light, it's going to appear red. Right? So think of it as the opposite of what you would expect. Nice and simple. Now, we use things such as ultraviolet visible spectroscopy to look at absorptions of energies, but reflectivity measurements are a lot more sensitive in that we had a red material at high temperature. At low temperature, we have a green material. Reflectivity is a reporter of everything that isn't absorbed. So at high temperature, the material looks red. At lower temperatures, it looks green, right? But what's interesting is at the very lowest temperature of the experiment, it was red. Well, something wasn't consistent. So what we decided to do was a different experiment where we focused on a single wavelength light shining on the sample. And lo and behold, the issue was much simpler to explain. It was red at high temperature. That's where we have the iron 3, cobalt 2 pairs. Low temperature, around here, becomes green. That's where we've done the electron transfer and we have iron 2, cobalt 3. But the light shining on the sample causes the electron transfer again as you get to colder temperature. Then it becomes red again. We can do that for all our samples. And depending on how intense light is, those curves may be offset or equal. Depending. All right, but this was the first time in a molecular compound that you could show photo and thermochromism that mimics the three-dimensional Prussian blue that I described earlier. All right, so crystallographic stuff. These are well separated in a solid state, meaning that the clusters really aren't touching each other. You have lots of counterions and lattice solvents separating these. Because of that, they behave independently from each other. Right, and that's important. That's an important theme. All right, better view is showing it like that. Again, the void space between those clusters are solvents and anions. And summarizing a lot of work, we showed at high temperature, near room temperature, it was red. We have rather long cobalt nitrogen distances that are reflective of this cobalt 2 high spin nitrogen distance. If we quickly cool it, we haven't given it enough time to relax. So we've trapped most of the electrons in the high temperature state. And lo and behold, it still looks red. The bond distances haven't changed. And more importantly, the cell volume, everything in there, is about the same. Now, if you slowly cool it, you give it time and enough energy for everything to wiggle about to condense the structure. And if you get electron transfer, what color do you think you're going to get? Lo and behold, clusters are green in appearance. Their crystals are green as well. But notice, right? Notice lots of things are happening. It's that single electron transfer between the cobalt and the iron centers is changing bond distances and angles a lot. And you're also collapsing the unit cell volume by quite a considerable margin. And that's because of removing antibonding electrons at the cobalt site. When you oxidize it, it goes low spin. And so in terms of the magnetic properties, just to remind you, it's red at high temperature, it's green at low temperature. If I have lots of unpaired electrons, I should have a high magnetic signal, which I do. Cold temperatures, everything should be spin paired, so the magnetism goes away for the most part. You can shine light on it. We do electron transfer, we get about 80% conversion, this red state. Or if we quickly cool the material, we get this blue trace. It's not as good because things relax. But what's interesting is, and we just counted this for a number of years, is that increase the temperature from 1.8 towards 300 Kelvin, the thermally trapped and photo-induced states relax at the same rates. No one had ever seen that before. And that suggests that there's some sort of vibrationally involved state separating the optically and thermally trapped in its relaxation. So comparing that to the three-dimensional Prussian blue, don't see long-range magnetic order because these are molecules. They have 8 spin centers as opposed to millions. We do see that paramagnetic state. The spins are schizophrenic and barely talking to each other. All right, and that mirrors what you see at high temperature in terms of its magnetic signal. Now we don't see this thermal hysteresis in the magnetic measurements, all right? It's because the molecules really aren't cooperatively talking to each other, this contraction and expansion. It's about 2 Kelvin. We determined that through other experiments, right? But this is the first time we've been able to mimic all the salient features of the three-dimensional Prussian. And there's the Arrhenius data showing the thermally trapped relaxation. So that is relaxation as you increase the temperature, or you follow the optically trapped data with respect to time. It's superimposable. Follows Arrhenius kinetics, so there's got to be some thermally activated state. And so for the first time, we showed that we could access the two states photochemically and thermally. We have a lifetime of 10 years at 120 K. That may not be of much importance to you, but I mentioned that magnetic hard drives have a lifetime for their data storage 10 years, albeit at room temperature. If you compare the molecular box that I was just describing, the three-dimensional Prussian blue, molecular box has a lifetime of 10 years at 120 K. But the Prussian blue analog is 3 days. So 8 metal centers does a better job than million. Talk about atom economical. All right, showing you other ways to make molecules. I'll just focus on the molecular squares for right now. So taking other arousal borates with now functionalities at these 3 positions, or the Z groups, as I mentioned earlier, they limit the numbers of available cyanides for bridging to adjacent. And in this particular part of the project, squares are the norm. And you'll notice that when you self-assemble these in a variety of solvents or capping ligands, you get these molecular squares where you have 2 cyanides bridging between the iron and the cobalt, and you have a terminal cyanide poking out into the outside world. And they're always anti or oppositely aligned with respect to each other, and that's to minimize the dipole moment. Right? And so that seems to be the norm. And despite what we try, and we can't get them to go cis. All right, so in the place of DMF, DMF is a good donor solvent. It's got a high dielectric strength. It's polar aprotic, has all the characteristics of a good donor ligand. But the nice thing about DMF is that it can be displaced for better sigma donor, better Lewis base. Think of the cobalt as. So by using 2,2 by pyridine, you take 2 pyridine rings and you fuse them at the carbons next to the nitrogen. This bite intake ligand is a nice, easily accessible and modifiable ligand to cap those DMF positions with more substitutionally inert ligand. And so here's just a nice cartoon showing you what showing you that this is what the BIP analog looks like. I'll talk about the properties of that in a minute. But there's also a lot of chemistry going on in the background. It looks very nice to say, magically, you throw all this stuff into the pot, and you get this cluster at the end of the day. Well, no, actually, that's rationalization after the fact. Here's just an example of one of the things along the reaction path. You can make bimetallic, where you have some ligand, either an anion or solvent or whatever. Sometimes you can isolate this and measure its properties. But when the ligand is labile, meaning it's easily removed, you get self-assembly to give a square or hexamers or other things. So there's a lot of chemistry involved, but people don't talk about it because it's complicated. So this is a chemistry project, so I like to highlight that. I wish I were that good. If I were, I would save a lot of time. All right, so in terms of compounds that have tris 3,5-dimethylpyrazyl borate, star, 2,2 prime by pyridines on the cobalt, and some anion, X. In the presence of 4 waters of crystallization, these water molecules can adopt various interactions with the anions, charge balance the complex. They can hydrogen bond to the cyanides. They can hydrogen bond to themselves. This is one polymorph. Polymorphism is a very important issue for pharmaceutical companies because the bioavailability and dissolution kinetics depend on how fast or slow the crystals go away in the body. Likewise, you get different chemical properties with regards to this project. These compounds all crystallize nicely. You can see these red lines are hydrogen bonding between red spheres. Those are lattice water. And triflate anions, trifluoromethane sulfonate, where the water molecules hydrogen bond to the oxygen atoms, that sulfate derivative, if you want to call it. Here's another one where you have hydrogen bonding between cyanides, lattice water, and triflates. There's one where we attempted to get rid of all the water and hydrogen bonding by inserting something called tetraphenyl borate, an anion, where you have a central boron with a formal -1 charge, and then 4 phenyl rings, C6H5 attached to that, anion. All the structures are different, and that was kind of annoying, but the important thing is, even if we remove the lattice water or other solvents or other anions, we got things that had different spectroscopic properties, but none of them showed electron transfer. But from electrochemical studies, we predicted that this combination of ligands on iron and on cobalt should do electron transfer. So something else is important. It's the structure. Right? And that had been underappreciated for a number of years. So our first foray into this was making a molecular square with the same bits, pp star on iron, pp on cobalt, triflate. But now instead of 4 water molecules in the lattice, we inserted DMF to introduce disorder. That disorder is important for this breathing of the complex. The absence of breathing, and if you have a rigid environment around a cluster, basically has congestive heart failure. It's not going to expand and contract. It's not going to do the electron transfer. So at high energy, you can see up here, this is the B8 stretch from the perazyl borate on the iron. High energy for iron 3, low energy for iron 2. Go from relatively high energy cyanide stretch, that's the bridging, that little blip there is the terminal. Remember, the terminal cyanides do this, relative to the plane of the square. And when you lower the temperature, lo and behold, the high energy absorptions go away. New lower energy ones increase of much higher intensity, reflecting that you did electron transfer. Now, again, we looked at crystallography, and we were the first, again, to show electron transfer from molecular square. So at high temperature, it's red, relatively long cobalt nitrogen distances. At lower temperature, quickly cooled, that is, red, not enough time to relax. But if we slowly increase the temperature, it becomes green. What we did is we tricked the system. What I haven't told you is there's a phase change between around 120 K's. Crystals shatter. You can see them explode under the microscope. What we had to do for this system, because we have these close contacts between the Bippy rings, now we have molecules talking to each other. So when they breathe, any strain induced from bond elongation or contraction is going to be communicated. So the problem here is that we had to quickly cool the material and then slightly titrate in some heat energy, allow it to relax. Right? Sometimes the crystals still explode, but it's allowed us to get an X-ray snapshot of the two states. And so you can clearly see that you get a contraction of the cobalt nitrogen distance, likewise the unit cell volume. We get the color change that we all expect. All right, to show you in more detail what's going on, focusing at 2 different temperatures, we have hydrogen bonded cyanide here. We still have one. We've removed the other one by putting in that DMF into the lattice. Iron-iron contacts and cobalt-cobalt contacts show you that the clusters are well separated. At high temperature, if you focus on this portion of the slide, focusing on the tricyanoferrate, right? In that you can see it rotates just a little bit. And the cobalt, a lot more is going on. All right, so that's the cost of doing business for that electron transfer. The transfer of that electron, one electron from the iron to the cobalt, causing tremendous structural changes and expansion and contraction of the molecule. Consequently, that leads to the energy barrier. All right, magnetic properties. Again, it's red at high temperature, green at low temperature. Lots of unpaired electrons. essentially zero. We can access this photochemically. We can quickly cool it. They're not superimposable ever, but again, we increase the temperature, follow Arrhenius kinetics. There's some sort of thermally activated state. We decided to substitute Bippy rings and put methyl groups on there to disrupt this pi-pi stacking interaction between rings on adjacent molecules. And we purposely chose putting methyls at the 4 position because it doesn't change the electronic properties, donor properties of the Bippies, but might impact the intermolecular communication between them. And so while it's difficult to see, at least on that screen, you might be able to see it here. Basically, this is very close contact here, and for here, these are slipped with respect to each other, slightly elongated. And that little difference makes all the difference. You see that the hysteresis for here with those closer contacts goes away as they become further apart and separated. We can still access the photochemical state, although it looks a little different at low temperature. That's an area of active research. Thermohysteresis went away, but more importantly, we have a compound now that's soluble, whereas the compound on the left is insoluble. We can dissolve it in solvents, and as we change the polarity of the solvent, we can change where the electron transfer happens. That is high dielectric strength solvents, particularly methanol, hydrogen bond to the terminal cyanides, and shift the redox potential to very high value. And you see a very high temperature for the electron. All right, another way to look at this is just put a capping ligand that bridges the face, top and bottom faces of the cluster. Again, the idea is to minimize the intermolecular interactions in the solid state, ideally decouple and make these things more squishy, making the electron transfer happen at higher temperature. So just doing some chemistry, you can take this substituted Bippy group. Instead of doing a methyl group here and there, we put this imine group. This gives us a lot of flexible spinach. And again, we shift everything to high temperature, consistent with the fact that we're giving it more room to breathe. Electronically, we haven't changed anything, right? But we did allow for a shift to higher temperature. And if you put different anions into the lattice, you can also change its transition temperature from very low values to much higher values, depending on the intermolecular count. All right, showing you the crystallography. Again, things wiggle when you do electron transfer. High temperature, it's red. Low temperature, it's brown. And brown is just somewhere in between red and green. Think of, Ziploc bags. Be a different color. But this transition occurs at about 230 Kelvin, and that's much higher than any other one. Once again, the chemistry matters if you understand the cost of doing business for the electron transfer. All right, one of the last compounds that we'll be doing is we wanted to focus on what kind of donor abilities are needed to do the electron transfer, and we wanted to focus at the iron sites. Many competitive groups focused on the cobalt site because they could buy their ligands from the chemical company. And we didn't want to get into that game. We wanted to do something more interesting. So we did more synthetic work to make new ligands, make new tricyanoferrate complexes. And during the course of the reaction, we could do lots of things they could. And so by taking this PP methyl or tris 3-methyl pyrazyl borate, it's less donating than the other ligands. The idea is we shift the redox potential for the iron in a more positive direction, then we should shift transition temperature where electron transfer happens to a higher temperature as well. Right? And so that was our working hypothesis. We kept the ligands same on the cobalt because we wanted to just change one variable. And our first foray into this, we found that you can get 2 different structures depending on order of addition and stoichiometry. If you add iron, or rather the cobalt to the iron, you get this as an anion, and you get a very complicated structure. You still get these squares interacting through the Bippies intermolecularly with each other. That's along the crystallographic B direction. But the anions here that are charge balancing these dications, hydrogen bond to lattice water, these green guys, those are the tricyanoferrate anions. They form two-dimensional sheets perpendicular axis of the wall. I was shocked that we got that. All right. More simply, we can use tetraphenyl borate, substitute those tricyanoferrate anions. You get a different structure, but you have molecular squares shown here, and tetraphenyl borates there. All right. And so for the first time, we were able to show not only can you get an X-ray snapshot as a function of temperature, you can also get it as a function of light. Right, so at 240, it looks like that. At 120, it looks like that. Again, things are moving. With light, you also see corresponding changes in the structure, all of which are reversible, depending on you obtain the data in the presence of light or absence, and at what temperature you obtain the data. So again, we're reaffirming that these compounds are accessible by temperature changes, light, it's all electron transfer. All right, complicated infrared spectra, but I thought I'd show you a little bit because hopefully you've seen that before. But infrared spectra is a nice, cheap method to assay whether or not you have electronic changes in your structure. And so we use this to show that at high temperature, we have very high energy stretch. It's mostly dominated by this anion. Like very close to room temperature, we see corresponding increases in lower energy absorption, which is due to electron transfer. In the tetraphenyl borate case, you don't have any cyanides to worry about, so it's much easier to understand. High energy stretches initially. Notice I have two now. That's interesting. We thought, hey, maybe we can make things that change electron transfer, do electron transfer in 2 steps. Turns out, no, not for this compound. But for others, we can. But suffice it to say, high energy iron 3 cyanide, cobalt 2 goes to iron 2 cyanide, cobalt 3, just as before, slightly different. Magnetic properties show a transition. The halfway point is here, called T1 half. For this anion substituted derivative, it's 230 Kelvin. This one is 244. And this allowed us for the first time to also describe that the anions, while they do play a role in the electron transfer, that's not the business end of the behavior. What's happening within the molecule. All right. How many of you have heard of electrophile? These are Lewis acidic things that tend to make bonds, Lewis acid-based combinations, donor-acceptor bond. So there are a variety of these available. Important thing is that these electrophiles can attach to something with a non-bonding electron pair, like a terminal cyanide, remove electron density, and that should change the redox potential of the cluster by induction. So we thought, all right, that's our square. We can think about this in terms of a state diagram where that's a long cobalt nitrogen distance and it's composed of these metal-metal pairs. If we add an electrophile, we attach it to the terminal cyanides. That should remove electron density from the iron and by induction, the rest of the cluster. Right? So I'm borrowing a little bit of Monty Python. We call it the holy hand grenade. Right? The electrophile does a lot. It removes a ton of electron density from the cluster. But in cartoon land, this is would be what you expect. You get a 2-to-1 ratio of electrophiles to cluster because you have 2 terminal cyanides. And now if you remove that electron density from the cluster, now you make it favorable for electron transfer to happen from here. And then down there, and then you get the iron 2, cobalt 3. All right, summarizing a lot of painful data acquisitions and experiments, you do see corresponding changes in the infrared spectra. When you add 2 equivalents, you have to have 2 equivalents of electrophile, else it decomposes. And there's an X-ray structure confirming that we have 2 electrophiles per cluster. And this is the tris pentafluorophenyl borane derivative. We can do this for other ones. Unfortunately, we're now in this hole. We can't climb out either photochemically or thermally without decomposition. So the electrophile worked well, but we don't have anything that's tunable. All right. Lattice disorder in breathing. Basically reiterating what I've said all along. If things are crystallographically ordered and you have close contacts between the reactive bits in the unit cell, You don't see any electron transfer. In the molecular box, we had disorder at these uncoordinated pyrazoles, and that was weakly interacting with its environment. We saw electron transfer. I highlight that the volume of solvent around the cluster is large, small in this case, where we didn't see any behavior changes. Likewise, in the Angewandte Chemie paper, 2010 paper, we see lots of action around BIPs on the cobalt, and suffice it to say, they're either doing jazz hands or they're doing this. They're either doing this or they're wiggling like that. That wiggling is giving you the volume space necessary to allow for the expansion and contraction. And lo and behold, solvent volume around that is large, further minimizing intercluster interactions that shut down your electron transfer. All right, so last compound, I think. You take this easy not TPME or tetra 3-methyl pyrazol borate tricyanoferrate anion. Treat that with cobalt-2 trifluoromethane sulfonate. Use our bipyridines again. We get something that looks like everything else. You might say, yeah, who cares? It looks the same. Well, the chemistry matters because the chemistry is changing the behavior. Structurally, the core looks the same, but the other stuff is mitigating the kind of behavior you're going to see ultimately. And so you see big changes in the infrared spectra. Because we had lattice acetonitrile, methyl cyanide, or solvent, that's this absorption here. It doesn't participate in electron transfer, so it stays put. It doesn't change when we change the state. But the cyanides involved in the bonding between the cobalts and the irons and the terminal cyanide change their energies a lot, again, consistent with that intramolecular electron transfer. The magnetic properties are pretty interesting. If we remove the solvent, you can see that it's relatively flat. It's trapped in this paramagnetic state, meaning that presumably the lattice has collapsed and you can't elongate or expand the cluster. And so the energy barrier is too high for it to do it, so it doesn't. But when you have the solvent molecules present, you get a two-step transition, suggesting that you have two energy costs for electron transfer in the same molecule. And if you look at the crystallography, you have one iron center and one cobalt center have a different number than the other two. That means they are crystallographically independent. And from the magnetic data, it suggests that maybe they have different energy costs for their electron transfer because they have different bond distances and angles. All right, showing you just the derivative to show you have two different thermal hysteresis. You have one with a very large one, suggesting you have lots of cooperativity between molecules. And then you have a much smaller one, suggesting you have very little. So as you can imagine, big thermal hysteresis takes lots of energy. Small thermal hysteresis, very little. Right? And so on that working hypothesis, you can see that's crystallographically. All right, you have red and green forms again, but I'm just going to highlight the light-induced structures. Focus on what's moving. Up here, these contacts between the coordinated bipyridine and one of the arms of the tetraphenyl borate don't change a lot. These change by quite a bit over here. Right? You might say that's not a big difference. Well, it's a big enough difference to see two-step behavior in the magnetism. You can see it crystallographically. And so, again, the chemistry matters, at least in our opinion. And if you understand the cost of doing business, you can do a lot of things other people can't. All right, so to show you the mechanism that's been proposed, all fine and good if it's just chemistry, but you need to understand the why. That's the most important part. This was formed by Bilal Malal in France and other coworkers. And they found that at low temperature, a technique called X-ray magnetic circular dichroism, right? And Zanes and XFs. For those who are interested, I can talk about later, but time considerations, not now. You have these low spin cobalt-3 iron-2 pairs. Shine light on it. You quickly generate an excited state cobalt-3, keeping the iron-2 in the same electronic state. So all you did was remove electron from the non-bonding P2G set and put it in the EG antibonding set. This quickly relaxes to give a new state where you have a high spin cobalt. Notice now you have, instead of one unpaired electron up here, you have two in the antibonding orbital and one in the, sorry, two in the, I can't see, two down here. Iron 2 has not been changed, so this is prior to electron transfer. And then the slow step is electron transfer from the iron to the, that is vibrationally gated, meaning that it goes through a vibrational state. And that's what we saw in the optically induced and thermally induced changes. That's the slow step in the reaction. That's the slow step in the electron transfer. That is what allows us to do anything in this project, because we do slow spectroscopy fast. So in cartoon land, you shine light, get electron transfer from the iron to the cobalt. You haven't given enough time or energy to relax, so you have a stable structure. That's why you have these bent cyanide bridges. And then with enough time, it expands the lattice, allows that electron transfer to complete its task to that vibrational state, which you can actually measure, and people have done that now. And to further illustrate that I think we have a good handle, at least from a molecular standpoint, I failed to mention that this was done on Prussian blue analog. For our molecular compounds, I think we have an analogous argument in the absence of their data, in that if you look at most of these, they have a unit cell volume, and more importantly, a volume of solvent around the molecules that's small, about less than 10. The ones that are 16 and 22 have much different structures and nuclearity. So they're the statistical outlier. Right? None of these show electron transfer, although the ligands, anions, and the metal centers present should allow for it in theory. Now, if you compare that to other compounds where you do see electron transfer, both magnetically, optically, and spectroscopically, you can see that the volume of solvent around those molecules is ginormous. Again, if you don't have room to breathe, you don't. You have to expand and contract, and the solvent molecules plastic enough to allow for that expansion. All right, so showing you just some metal ligand trends. There's a Goldilocks zone in all of this, and that if you have a very good donor on iron and a moderate donor on cobalt, you don't see any electron transfer. In other words, you're trapped in that state. Can't reduce the iron further. It has too much electron density. When you remove some electron density from the iron at the arousal borate sites, keeping the ligands on the cobalt fixed, now you start to see electron transfer. Now they're close enough in energy that you can access it by temperature change. And as you might imagine, can you go the opposite direction and get yourself into a hole again? Yes. If you have a very electron poor donor on iron and a very good electron donor on iron, 910 phenanthroline, nevertheless, phenanthroline, you're now in the opposite case. You're in this hole, can't climb out of it. Consequently, you don't see the electron trapped in the iron 2 cobalt. All right, and so as a general trend, as you decrease the donor on the iron, increase the temperature where you see electron transfer, there's no mystery about it. It's just chemistry. So I'd like to summarize by saying, hopefully I've convinced you that you can exhibit reversible, tunable, and thermo and photochromism as a function of chemistry, but also understanding the environment around the clusters. Of course, these optical and magnetic properties are associated with electron transfer. If you don't see or experience electron transfer, you don't see the corresponding color and magnetism. Both the solid and solution state structures are important. You can tune this by, again, chemistry, ligand substitution, solvent dielectric, what have you. And as a consequence, of course, everything has to be tunable by the above. And we have the ability to tune both the redox potentials and a solid state environment at will, because we've spent the time to learn the chemistry. More importantly, the self-assembly and crystallography, important for the project. With that, I'd like to thank Grifty for the invitation, the organizers, if there were any, and you for your time and attention.